Hi, I'm Jessica Flesher. I'm a graduate student in the Ganesan Lab at the University of California, Irvine. Humans have a wide range of skin tones. These tones are a result of different amounts of the pigment melanin in our skin. There are those, like me, who have very little pigment and light skin. Others have lots of pigment and dark skin, and there is every shade in between. What this means is that everyone has their own unique amount of melanin. But skin color can change. This can happen intentionally by staying outside in the sun to get tan. However, tanning has an unwanted side effect: skin cancer. The lighter your skin, the higher the risk. Why? Pigment protects skin from damage caused by the sun, so darker skin with lots of pigment has more protection. Changes in skin color can also be caused by pigmentary disorders. Individuals with vitiligo lose skin color in areas where pigment is no longer made. This can happen on the hands and the face, making vitiligo a very visible disease. Current treatments may work for a while, but they can cause rashes and even make the disorder worse over time. So, can we find a way to tan skin without causing damage? When you think about human skin color, it is important to remember there is a lot of variation. As I mentioned, melanin helps protect against skin damage caused by UV light from the sun. However, UV light is needed to make vitamin D, which strengthens bones. So, too much pigment stops the skin from making vitamin D. That is why humans, traditionally from areas with less sunlight, have lighter skin. So, how does the pigment in our skin get made? Our skin is like a valley. It spreads out over large distances and is divided into individual sections. Most of these sections are regular skin cells, or rather farms in our valley. But these farms are not completely isolated. There are also small towns. These towns are like specialized skin cells that make pigment called melanocytes. When you go outside in the sun, what happens to this peaceful valley? UV light hits the skin. This would be like aliens, descending from the sky and attacking the farms. Buildings are destroyed and fields are left smoking. In other words, the skin is damaged. The farms send a message into town for help. The sheriff responds by training deputies. These deputies are the pigment. Trained deputies are sent to the nearby farms and the skin gets tan. The next time the aliens attack, the deputies protect the farms, just like the pigment from a tan protects your skin. So, researchers know the overall process of how pigment gets made. If we go back to the valley, we know the message the farmers send to town, we know who the sheriff is, we know the steps required to train the deputies, and we know that the deputies protect the farms from future attack. One thing we don't know is how the deputies receive the necessary supplies to train. That's where my research comes in. Melanocytes have to deliver everything to make pigment to the place pigment gets made. My research focuses on a protein called whippy that may act as a delivery man. So, does whippy affect skin color? To answer this question, I use mice. Mice also use melanin to create their coat color, but there's just one problem. Mice only have pigment in their hair. So how do you measure how much melanin is in mouse hair? You collect the hair by shaving mice. I collected hair from two types of mice: mice with whippy and mice without whippy. Mice without whippy have less pigment in their hair, about 15% less than regular mice. So, what does 15% less pigment look like? Well, regular mice with whippy are normally black. Without whippy, the mice look black. However, we know loss of whippy reduces the amount of pigment in the hair. But to produce convincing evidence, I need a distinct change in coat color. If we go back to our valley, what would happen if the sheriff can't set everything up to train the deputies quickly? You would expect that it would take longer to train the deputies to protect the farms. With this delay, any change in deliveries would have a larger effect. In pigment cells, the sheriff is called MITF. MITF turns on the production of pigment after receiving messages from regular skin cells. So, what would happen if mice without whippy have half the normal amount of MITF? I expect that these mice will have less pigment and gray hair. So now I wait, looking for a gray mouse. This gray mouse will help us understand how whippy helps skin tan in an organism. Additional research will focus on what whippy is actually doing when pigment gets made. Further studies will help us understand how whippy 1 recognizes the correct delivery truck, identify what whippy 1 is delivering, and address how to make whippy 1 more efficient, all to identify if whippy 1 is a good target to change the amount of pigment in skin. If we can increase the delivery of supplies to make melanin, we can develop new drugs that target whippy 1. These drugs will help prevent loss of skin color for those with vitiligo, and they will help individuals with lighter skin tones to prevent skin cancer. So, here's to the future of protecting our skin using our own pigment, even for those, like me, who have very little, so everyone can enjoy their days in the sun.